Okay, the second speaker this morning in this special occasion in the Symposium on Analysis and Geometry uh, is Dr. Denny Ivanal Hakim. Dr. Hakim got his first degree from ITB in 2012 and his master degree from ITB also in 2013. And then he went to Japan for his doctoral degree and he obtained his doctoral degree from Tokyo Metropolitan University in 2018. He's now the head of the undergraduate program here, and his research, his main interest is in Fourier analysis. He has some works on fractional integral operators, interpolations of Morris spaces with variable exponents, and also regularity of the solutions to some elliptic PDEs in generalized Morris spaces. He has written a book, Morris Spaces, Introduction and Introduction to Integral Operators and PDEs. It's a two-volume book published by CRC Press in 2020, co-authored with Professor Sawano, his doctoral supervisor, and Professor Basio. So today we'll speak about estimates for risk potentials via the risk transform. Please.
Thank you, Hendra, for the introduction. Yeah, first of all, I would like to thank our guests once again, Professor Schikorra and Professor Riesz for his attendance in this mini symposium, as well as the participant in this symposium, our students, as well as other lecturers from ITB, as well as other universities, and also participants in the Zoom meeting. Yeah, today I would like to discuss the topics about the estimates of fractional integral operators by the norm of Riesz transform.
But Denny, I think you can open it.
Sorry.
You are quite far from us. It's safe.
Right, safe. Yeah, I think that's the idea for the history here. I learned the topic when I was attending the online seminar, and at that time the speaker is Professor Denny Spector. He gave a lecture about this L1 estimates of fractional integral operators by considering the Riesz transform. And yeah, his research was joint work with Professor Schikorra and Jan van Schattingen at the time. So I'm interested with the problem, and we discussed it with students. And that time is Muhammad Jamal, former student of Hendra as well, and then Dr. Daniel Salib, the lecturer in Parayangan. And then we consider several continuation for this topic, as well as the extension in other function space and other consequence with some other colleagues, and including Pak Wano, because at that time we supervised one master student together, and then other master student, and currently we work with Irfan to this problem. Okay. So here is the outline of the talk. First, we like to recall the introduction to this topic, namely fractional integral operators and fractional maximal operators. And then see some norm estimate of this as a previous result, and then we will consider some applications of or some consequence of L1 estimates of risk potentials. Okay, and then more currently we also work in Lorentz space as well, and then we'll see some concluding remarks and discussion for other direction of this research. Okay, so start with the usual definition of the fractional integral operator, or sometimes we call this as a risk potential. We start with alpha is between 0 and n. Then the fractional integral operator I alpha is a map that sends the function f to the function I alpha f, and I alpha fx is defined to be the convolution of f with the kernel x to the power alpha minus n, okay, for a suitable function of f, so that this integral converges. Okay. Yeah, we can start with the f in c infinity c, for instance, and yeah, this operator is known to be bounded from LP to LQ, where P is in between 1 until n over alpha, and Q is defined to be 1 over P equals to 1 over P minus alpha over n. Then, the thing is, when we consider P equals to 1, the issue is that this operator is not bounded from L1 to Ln over n minus alpha, so P equals to 1 and Q equals to n over n minus alpha. And the reason is that we may take, for instance, the characteristic function on the unit ball is in L1, but its mass is not in Ln over n minus alpha. So so the question is, can we substitute the right-hand side of the inequality, the usual boundedness condition of I alpha? So we can replace the norm of the L1 norm of f by the norm the L1 norm of other function there. Okay, and this is another operator, fractional maximum operator, defined like this one. So in the definition here, we can think of the limiting case where alpha equals to 0 as the supremum of the average of absolute value of f taken for all ball center at x of radius r, and the fractional one just modify the average by the power n minus alpha there. Okay. And from the relation between fractional integral operator and fractional maximal operator, you'll see that fractional integral operator can dominate the fractional maximal operator. Okay. And of course, in this case, the boundedness of these operators can be followed from this pointwise estimate. Okay. So that's the two operators that we consider here. Okay, so if we go back to the case where we consider the boundedness of fractional integral operator, actually there is a consequence of the theorem of the boundedness of fractional integral operators, namely we call Sobolev inequality, or usually Hardy-Littlewood Sobolev inequality. Namely, if we take alpha equals to 1 in this case, and P is strictly greater than 1, it's less than n. So Q is it's 1 over P minus 1 over n is 1 over Q. So Q equals to NP over n minus P. Then if the gradient f is in LP, then f itself is in LQ. Okay. Yeah. But if we compare this with if we see this Sobolev inequality as the consequence of the boundaries of integral operators, we lost the case where p equals to 1. So, yeah, although it's not bounded, later on, the case where q equals to 1, the case when p equals to 1, for this inequality is still correct. And the replacement is that if, yeah, the gradient f is in L1, f is in still Ln over n minus 1. Okay. So there is a constancy such that the Ln over n minus 1 norm of f is dominated by the L1 norm of gradient of f. All right. Okay, so the question is, yeah, can we, in some sense, use this information to fix or to improve the inequality for the case p equals 1 for fractional integral operator, at least for the case alpha equals 1. Yeah, in that case, if we take alpha equals 1, we have a alpha equals 1, then replace f by I1f, okay, and to calculate the minimum inequality, we obtain this one. And then if we see the term gradient I1f, so we consider the partial derivatives, okay, interchange the order of the integral and differentiation, we get this expression. And this expression is called the J component of the Riesz transform. Okay, so RJF is the one on the right hand side. Then we get this one. So the third expression here, this inequality, tell us that if alpha equals to 1, then we may have a substitute for the failure of the boundedness of fractional integral operator. So we'll see that in this case, yeah, in this case, it's not f, but the maps of the Riesz transform of f. We calculate now in L1. Okay. Yeah, actually, we learned this kind of idea in a remark or in the notes of the paper of Professor Schikorra-Spector and Jan van Schattingen. So I recommend to read that manuscript to learn besides the result as well as the remarks and the technique for get the intuition of this problem. Yeah, and actually for the full bridge of B, at least for the case where we can substitute the right hand side here, there is a result by sine and y. Sorry, this is just a mixed notation, but to not confuse with this is just we take the norm of RF before we calculate its LP norm. It just mix the notation, and the result is that yeah, in this case the inequality also include the case p equals to 1, but and then alpha is quite is general in the range of between 0 and n. But the difference between this one and the last inequality is that the right hand side here is the sum of LP norm of f and LP norm of RF. Okay. Yeah, yeah. I think up to my knowledge, this one is the earliest substitute for the Hardy-Littlewood Sobolev inequality for the case p equals to 1 with this modification. this is Stein and Weiss. Okay. And yeah, as notes, yeah, one of the definition of the Hardy space using this condition that this is finite. Of course, there are later on other equivalent condition for the Hardy space. Okay, and for the case where p is strictly greater than 1 and less than n over alpha, it is consistent with the Hardy-Littlewood inequality because we may use the boundedness of the Riesz form for this range of p in LP. Then in that case, the right hand side becomes the LP norm of F only. Okay. So this inequality can be read in the complete form when p equals 1, because when p is greater than 1, the right hand side remains to be the LP norm of F. Yeah, as far as up to my knowledge, I think that after that, the refinement of the inequality is the result in 2017 by Professor Schikorra-Spector and Van Schaftingen. And yeah, the idea is that for the case where alpha is large, meaning alpha is greater than 1, is by combining the case alpha equals 1 and then the boundedness of fractional integral operator with index alpha minus 1. So, so that's the idea, because we have the case alpha equals 1, and then yeah, we want to consider all the general range of alpha. So we start with alpha greater than 1, and we use the generic property of symmetrical property of I alpha. Yeah, I have to admit that if we start with the definition of the fractional integral operator without a constant, so we have to as a constant. Okay. Yeah, and constant only depends on the dimension and alpha 1 and alpha 2. Okay, and okay, so in that case, if we start with this inequality, the previous inequality, and then we want to extend it to the case alpha greater than 1, we write I alpha as the composition of I1 followed by I alpha minus 1. And then the next step will be to consider the boundedness of the operator I alpha minus 1 from Ln over n minus 1 to Ln over n minus alpha. And the function involved here is I1. Okay, so that's Hardy-Littlewood inequality for alpha minus 1. And then the next one follows from this inequality. Okay. Right. Yeah, and then in this paper, it extends for all range of alpha, especially the detail is worked in the case where alpha is between 0 and 1. Okay. And what is the improvement from the previous result is that the right hand side here is just L1 norm of RF. And if we compare with the earlier result by Stein and Weiss, the left hand side, sorry, the right hand side is the sum of L1 of F and L1 of RF. Yeah, we'll do the left hand side is the same. And we see that this is an improvement because it's smaller. There is no L1 norm of F then on the right hand side. Yeah, the detail here is using the concept of the duality in Lorentz space as well as the boundedness of the Riesz form in the Lorentz space, and there are several calculations with Fubini theorem as well, and how to interchange the order of the integral and the operator of I alpha transform as well. And then also some technique for boundedness of Hardy-Littlewood maximum operator. And also another result is if we look at the left hand side there, the norm is in Lebesgue space, and after this research, Professor Spector proved the case where the left hand side is in so-called the Lorentz space with the index p equals to n over n minus alpha. Mix p and q. The first index is n over n minus alpha. Second one is 1. Okay. We have here the definition of the Lorentz space. Based on this result, based on this inequality, we try to prove the analog inequality when the case of the right hand side is in L1 norm. For example, if we have the boundedness of fractional integral operator, we may obtain, let's say, the so-called Olson type inequality of fractional integral operator. The idea is that we want to estimate the norm of the left-hand side of the product of some, usually we call some potential or some multiplication operator G, and then the fractional integral operator of I alpha f. Then we want to estimate this norm with the norm of G and with the norm of, let's say, f. But if we are starting with this inequality and the case where the norm is in L1, then the right hand side should be the L1 norm of RF, and then we have the L sum number of function G. And to do that, of course, we use the Holder inequality in that case. But let us see. As well as the fractional maximal operator. Okay, as a consequence, we get this one. From the previous inequality. So of course, if we do the directly the pointwise estimate of fractional maximal operator with the fractional integral operator, the difference that the right hand side is the R of absolute value of f. Okay. So we try to consider a little bit variation with this using the so-called Hardy-Littlewood maximal operator and sharp maximal operator. And the one that I mentioned here in the order is that we have this one. Especially the inequality 2 here. As a variation of the previous inequality, now on the left hand side we consider the L1 norm of G times I alpha f, okay? And we want to consider what happened with the right hand side. What is the right hand side? And we obtain the following inequality. So G is in weak Lebesgue space Ln over alpha, and the other term, another term is L1 norm of RF. And yeah, if we compare this with the previous inequality of Olsen type inequality for fractional integral operators, usually we have some LP norm of f here, and yeah, this is the same LP norm, but G here is in a certain Lebesgue space. It's not in a weak Lebesgue space, and yeah, if we compare this, then we'll see that the weak Lebesgue space is larger than Lebesgue space. So we have more option for G as the to multiply with I alpha. So although we have yeah, the right hand side is not exactly the Lebesgue norm of F, but L1 norm of RF. Okay, but usually we can yeah, in this usually we have a Lebesgue norm of G, but now we have a weak Lebesgue norm of G. Okay, so yeah, that's the trade-off of this inequality. So the idea is to consider the elder inequality. So we have the elder inequality in a Lorentz space. So G in this case, in this space, and then we have I alpha f in the case Ln over n minus alpha comma 1, and then we use the result by Spector to have this inequality. And yeah, the second inequality for fractional maximal operators follows with the same idea, but we use the inequality for fractional maximal operator. All right. Yeah, as an example, here we may consider gx equals to absolute value of x minus alpha over n. It is not in ln over alpha, but it is in ln over alpha comma infinity. Yeah, and then yeah, before we continue, we also remark that in this paper we also derive several inequalities, but the starting point is the result by Spector. We consider an application, a consequence in a fractional integral operator, fractional maximal operator, as well as the Olsen type inequality in some forms. And another one, we may consider the case of commutator here. So the idea is that we consider the commutator, but I have to admit that this result is quite restrictive because usually we consider the condition for the commutator is in a BMO classes, but yeah, we slightly yeah, first if it's in L infinity, yeah, we may consider some consequence of the endpoint case of this, and then yeah, if we recall the definition of the commutator is that we first multiply p to I alpha f and then subtract it with the maps of I alpha of bf. Okay. Then with this condition, we get this inequality for commutator. Yeah, and then currently we try to work on the estimate of in the Lorentz space here. of course, if we look at the first terms, the first statement is result of a spectrum in 2020, but we try to give a alternative proof and some partial case following the idea of Schikorra and spectral and concepting. Hopefully, we can obtain the more elementary proof compared to the proof of spectrum. But today I checked with Professor Schikorra. Thankfully, he gave some correction that we want to follow the revision to work with. Yeah, this is the case. Yeah, for the case when alpha is greater than or equal to 1, everything follows from the idea, the earlier idea in a Lebesgue space as well, but now applied for Lorentz case. And for the smaller case, we try to adapt the proof of the paper as well for small alpha, but we only arrive at the case where Q is not 1, Q is greater than 1. If Q equals 1, then this right hand side is L1 norm of RF. So we get the previous result by spectrum, but unfortunately we only arrive at this up to some correction, of course, later on. Yeah, that's the progress of this work. And that's good. Oops. Where's your self-facing? Okay, so sorry, there is a problem with the connection. So as I mentioned, the idea is that for alpha equals to 1, follows from the Gagliardo-Nirenberg type inequality. But it's slightly different here. Slightly different. The inequality, the norm of U is dominated by the norm of gradient U in L1. Instead of Gagliardo-Nirenberg inequality, we use the inequality in literature. It's called Alfino proved by Alfino. The difference is that previously we have the norm inequality of U Ln over n minus 1 is dominated by C, gradient of U L1. But the variation to this is this norm. The difference is this one. Okay, so we apply this and then for substituting this, and then we get the left hand side, the right hand side. This one exactly follow the idea of the previous results. And then once again, we consider the semi-group property with I alpha minus 1 and I1. Okay, and then now instead of Hardy-Littlewood Sobolev inequality in the boundedness of I alpha minus 1 in the Lebesgue space, we use the boundedness of I alpha minus 1 in the Lorentz space as a variation. fortunately we obtained a similar result. Okay? But yeah, the inequality itself is proof for full range of alpha in between 0 and n. We only just cover the case when alpha greater than or equal to 1. Yeah, considering some more elementary inequality one there. Yeah, for the second part of the theorem, for the second part of the theorem, we uh, yeah consider this case. So we try to adapt the earlier idea here by the duality of the Lorentz space. Okay, so that to calculate the norm of the quasi-norm of the Lorentz space by considering this expression, we may assume phi to be a smooth function with compact support as well. Then try to use the Fubini's theorem, and then apply the identity for the Riesz transform, okay, to obtain this one. Then yeah, use this proposition. Okay, so yeah, in the morning I discussed with Professor Schikorra. Might be we have to check the proof of the proposition so that yeah, try to see whether it works or we need to replace the statement of the theorem as well. Okay, but if yeah, for the Lebesgue space it works, but we have to check the condition in Lorentz space, and then by using this proposition, replacing phi and Rg of phi, we get this one as well as the boundedness of the Riesz transform in Lorentz space. Then if we summing over all index j, we get this one. Okay, so that's the result for in a Lorentz space. So yeah, if we start from the first result, we may yeah, this kind of discussion gives us this kind of result, L1 estimate by Professor Schikorra et al. Give or open the possibility to extend or apply it into many situations. For instance, for fractional maximal operator, as well as the multiplication operators, it also need type inequality, as well as commutator, and yeah, another type of estimate in Lorentz space. And yeah, actually, before we work with Irfa in this direction, we also work with Medita Kumala on the context of weighted Lebesgue space. Yeah, at that time we uh, find we found this paper by Lacey in the case of the Gagliardo-Nuremberg inequality, but on the weighted Lebesgue space. Okay, so as a reminder of Professor Schikorra this morning, we have to be careful with the case where p equals 1. We will see that on. And then we obtain partial results. Again, yeah, we still restrict the case when alpha is greater than or equal to 1. So if we apply this inequality, then we get the estimate for alpha equals to 1, just like before. Assuming the weight is in the case A1Q, and then for extending to the case alpha is greater than or equal to 1, sorry, alpha is greater than 1, we combine the semi-group property, it's like before, for I alpha minus 1 and I1 to combine this inequality for I1 equals for alpha equals 1. As a consequence of this, we use this one, and then the boundedness of I alpha minus 1 in the weighted Lebesgue space using this so-called APQ condition. Okay. And yeah, the result is quite restrictive because the assumption of the weight is in the intersection between these two classes. The first class is A1 comma n over n minus 1, and the second class is n over n minus 1 comma n over n minus alpha. Okay. Yeah, and yeah, we may wonder, is it natural assumption because usually for the boundedness of fractional integral operator, the condition is just the weight is in MPQ where p is greater than 1. Okay. So yeah, of course it's quite uh, tempting to compare this with the case where p is greater than 1 and p equals to 1. Because if we look at the previous result in Lebesgue space or in other Lorentz space as well, usually the condition just follow as a limiting case of it. But in this case it's strange because we have this intersection. Of course, if we can prove whether this intersection is can be comparable with a of p comma q, where p comma q is a limit of the case where p greater than 1, then it's all right. Okay. And then the other thing is how to extend it to the case where alpha is less than 1, because it's more difficult, as we saw in the earlier case. So when alpha is greater than 1, we can use the boundedness of the operator I alpha minus 1 and then use the base inequality where alpha equals 1. And then also the question is, can we extend it into for other function space, for example, Morris space, or weighted Lebesgue space here, or other function space that it's natural to see this as the extension of the boundedness of fractional integral operators. Okay. Yeah, I think that's all for the presentation. Thank you for listening. Thank you.
Okay, time for questions. Yes.
I'm very curious about the Mori space. I mean, you do the weights, okay, but the Mori space inequality. If you assume you're in this weird L1 and the supremo over the balls, then the Riesz potential isn't something. Have you ever thought about to prove that, and then if you assume the Riesz transform is in the Mori space of L1, hence you have the Spector type result?
Yeah, we tried with the case of Morris space, but if we just use the estimation directly in the normal ball, the constant can depend on the ball, but we do not know the dependence of this one. That's the one thing, and then. Previously with Professor Sawan, we also considered another approach by considering like a subharmonic function approach. But after that, after our discussion, he gave a presentation. I think it's online with Professor Spector, and he pointed out there is error in the argument of the subharmonic function that approach. And yeah, and we haven't revised the approach up to now. Maybe if one can, let's say, try, we try to do the estimated Morris space, but maybe start with the right hand side in the type of Stein and Weiss. Still, there is the norm of F on the right hand side. Yeah, because the problem is also we do not have the duality, just like in a Lebesgue space, in a Morris space. Yeah.
So do you have this inequality with the F and the Riesz transform of F in Mori 1?
We do not have. We want to try it, but still, how to remove the dependence on the ball.
Yeah.
Yeah. Because the norm is we consider the integral on the ball, but we have to take the supreme. Yeah. We cannot do it up to now.
Another question?
Yeah.
Yes, please.
Just curious for what is the difficulty for alpha less than 1 in that?
Alpha equals to 1?
No, when alpha is small, when alpha less than 1.
Less than 1. Okay. So we haven't actually tried the duality in weighted Lebesgue space, and some calculation maybe be wrong. We get the restrictive condition, namely W is bounded and 1 over W is bounded, and turns out, of course, it's only a constant or some oscillation like it. But for the general case, we haven't tried the approach of Professor Schikorra in the weighted Lebesgue space directly. We haven't tried the detail, as well as we do not know how to estimate or improve or adapt the idea of a specter in the case of weighted Lebesgue space. We haven't got the idea how to work the calculation in the context of weighted Lebesgue space. Because I do not know how to separate the weight if we consider the calculation like this type of calculation might be the weight involves there. But in this case there is no weight. We can interchange the integral. We haven't got this. Sorry.
So for alpha equals 1, you have this beautiful proof by Nuremberg, Galliano, which is essentially the fundamental theorem. Right? And u of x minus u of y, u prime, use this in the right way, you get this inequality with the right inequality. I mean, you get the sharp inequality. And so for alpha larger than 1, you can kind of work by balance. For alpha less than 1, you don't have that fundamental theorem, so you have to do the spectral approach. That's complicated. That's kind of based on von Schaftingen versus Mugen and Esken. There's some slicing involved. It's a very different taste of a proof.
Even in the non-weighted case?
Yeah, even in the non-weighted, and in the non-weighted case, Daniel Spector kind of solved it, right? But you have this big difference in the proof alpha larger than 1, which is based on the Nuremberg argument, which is like elementary but beautiful. And then for alpha less than 1, you need a completely different argument. It's essentially Spokan versus Merkowitz and John von Schaftings.
Any more questions? Denny, I just want to ask, do you know if there is anyone or any work on the discrete version of the fractional integral operator uh, in this direction? Using the Riesz transform. Discrete fractional integral operators.
Yeah, up to my knowledge, we do not know the type of the result, but some other result by Spector and correct is it's not just L1 estimate in Rn. I think in another setting you also write in a separate paper. But of course, if we think of discrete version, we do we replace the integration by summation, and the definition of the Riesz transform can be different. Up to my knowledge, we haven't seen this type, and also interesting because the discrete analog of fractional integral operator is I think you cite Peirce or Stein or in the introduction of discrete Morris space, you mentioned that there are several discrete analogs.
Steinwise.
Yeah. But we haven't seen this kind of inequality.
Okay, sir. Okay, no more question. I think we give another big applause to. Thank you. But we don't have souvenir for you. I'm sorry.
I can ask this secretary.
So, I will ask you to join lunch with our guests.
Thank you.
After this session. Pateo, will you come also? And some of my students. You are invited to have lunch with us. We have 10 minutes to clean this up, but we come back at 2 o'clock in the afternoon for 2 more talks. Professor Schikorra will give a talk, and I will also give a talk at the end of this symposium. Thank you very much.